My people, how are we? Today, in this video, I'm going to be, in this video, the ones that follow it, we're going to be reviewing some of the factoring techniques. This is sort of the second part of our calculus readiness review unit, just making sure, especially the more difficult ones, and especially when the expressions that we are given require us to employ multiple strategies of factoring in order to change the form, right? At that point, just a review of these is going to be helpful, so let's go ahead and jump right in. Now, let's go ahead and enumerate all of the factorization techniques, at least the main ones that we've talked about. That you've learned, over the course of your Algebra 1, Algebra 2, and Pre-Cal existence. Now, the easiest type of factoring, which is also the easiest to forget, and I cannot stress that enough, is your greatest common factor, okay? So greatest common factor is the easiest to do and the easiest to forget, because basically what this is undistributing. Okay, you are taking things and you're sort of perceiving them as, oh, if I look at this expression and I assume that there was a value that was distributed across all terms, then it must be a common factor of all terms. I can undistribute it, and that's basically what GCF is. So if you're given something simple like, 2x squared plus 8x, I noticed that, 2x times x and then 2x times 4, right? That is 2x is the common factor of both of the terms, so I can, like I said, undistribute it or factor it out, and I get 2x, x plus 4. Okay, well that's easy enough. And of course, this is quadratic, but it doesn't have to be. Some of the other strategies that we will discuss and you've learned in the past deal strictly with things that are quadratic in structure or what I sometimes refer to as quasi-quadratic, okay? And so they aren't technically a quadratic, but they have a quadratic form to them. And so if you have something like, and let's do dots first, which of course you remember as the difference of two squares. If you were given something like 4x squared minus 9, both of those terms are perfect squares. That is 2x squared minus 3 squared, and that factors into 2x plus 3 and 2x minus 3. Now the reason why that happens, as you know full well, is our factorization techniques come from when people would multiply, because remember, factorization is simply unmultiplying. So it's actually kind of similar to, it's a form of division if you kind of think about it that way. If you unmultiply, then basically you do so based upon the patterns that have been perceived from lots of multiplication. And they noticed that every time they multiplied a plus b and a minus b, you got, when you started to FOIL, right, a squared, and then the outer is minus ab, and the inner is plus ab, and then the last is minus b squared. When it was of the form of a plus b and a minus b, these middle two terms always canceled out. And if they always canceled out, then the product was always of the form of a difference of two squares. Well, as I told you a couple times already, and I will continue to harp on, the logic of these things run both ways, right? We know that if we have something like this, it factors like this, and we know that if we have a product like this, it multiplies out like this, and we need to remember that that knowledge that it runs both ways is extremely important. We'll get to more examples of all of these. I just want to lay out the basic ways of factoring and with one example, and then we'll go back and we'll just do a whole bunch of practice. Now, obviously, from there we have quadratics that are not we have quadratics that are not binomials, right? That are not the difference of two squares. And remember, like the sum of two squares does not factor, right? Sum of two squares doesn't factor. But among the trinomials, sometimes that's broken down into three different varieties. The first is also based upon a pattern, and those are basically the factorization of the perfect square trinomials. Okay, if you can identify a perfect square trinomial, then obviously you're going to have an easier time factoring. Now, obviously, strategically, this comes into account when we're dealing with completing the square, right? You know that a perfect square trinomial will always have that predictable structure to it, and that predictable structure to it allows us to turn it around and use it to solve by completing the square, but we'll talk about that another time. Perfect square trinomials are anything of the form that has, x squared plus or minus 2a as a coefficient for that linear term in the middle plus a squared. And that will always factor to x plus or minus a squared. And again, the formula, or if you can call it that, comes from just recognizing patterns from doing the multiplication a whole lot. And if you recognize the patterns from doing a whole lot of multiplication, you can use those patterns when you want to unmultiply, or in this case, factor, right? So if you have x squared plus, let's do 18x plus 91, you basically need to identify that as 2 times 9 and identify that as 9 squared. And once you do, it should be really, really easy to call that x plus 9. Sorry, that should be 80. Should be 81. That's what happens when I get going too fast. X plus 9 squared. Okay. And of course, it also is the case when it's got a leading coefficient other than 1. So if you have something like 4x squared and you have 49, obviously, because if this is a perfect square trinomial, the leading terms of both of the binomial is going to impact the outer and the inner products, which then combine into this middle term. And what you have is 28x. And the reason for that is if this is of the form a squared x squared, and this is of the form b squared, the middle is not 2ab. The middle is, no, it's not 2a, it's 2abx. And this, of course, needs to become ax plus or minus b squared. So in this case, this is, your a value is 2, your b value is 7. So 2 and 7 is 14. That is double that product. And therefore, this is 2x. And then, I shouldn't have put plus or minus here for the ones with actual numbers, but becomes 2x plus or minus 7. Okay. When you get beyond the perfect square trinomials, sometimes it becomes a little more difficult, but we'll go ahead and we'll sort of review that at the risk of insulting your intelligence. And of course, so basically we've done GCF, we've done difference of two squares, and we've done identifying perfect square trinomials. Now we need to be able to factor two different varieties of quadratics. And this is basically the quadratic factoring, normal quadratic factoring for, the trinomials. And the first one is when it is just x squared plus bx plus c with a leading coefficient of 1. So if we're just doing that, and we have something like, I don't know, let's say x squared minus 9x plus 14. Okay. Now, of course, you should be able to see this right off the bat, but just to remind ourselves what we used to do is, you know that what made this product, so this basically is a product of the same two numbers that this is a sum of. So, okay, well, why not just go ahead and start listing the factor pairs of 14? I can arrive at 14 as a product with 1 and 14, negative 1 and negative 14, 2 and 7, and negative 2 and negative 7. Now, thankfully, 14, not prime, but it doesn't have that many factor pairs, right? And so basically, of these four factor pairs, which one gives you a sum of negative 9? And it's obviously that one right there. And so you have x minus 2 and x minus 7. Now you get into a little bit of a conundrum when you have a leading coefficient that is not 1. And I showed you the AC method basically as a warning of, do not use it. And if you're given something like this, there are easy ones. If we're given 5x squared plus 2x plus 7, well, actually, that one's going to be prime. Let's do a different one. Let's say that we were given 2x squared plus 9x minus 5. Does it factor? And if so, how does it factor? Well, the great thing about this, and which is not always the case, is that 5 is prime. 2 is prime. And so you know that it has to break down into 2x and 2x. You know that 5 has to break down into 5 and 1. You know that one of them's positive and one of them's negative. The question is, does the 5 go here or does the 5 go here? And then once you figure that out, which one is positive and which one is negative? Well, 9 right here gives me a clue because I know 2 times 5 is 10. And that's just 1 away from 9. So if I actually put plus 5 here and minus 1 here, I know that I'm going to get 10x as an outer product on my FOIL, and I'm going to get negative x as my inner, and that is indeed going to sum up to 9x. Now we'll deal with ones that have leading coefficients and constants that are not prime here in just a moment, and talk about how to reason those out. But I certainly wanted to give you a heads up on all of that. Now, there's a couple more factoring techniques that we need to review. One of them, which I'm sure we all really enjoy, is grouping. Okay, now grouping, and basically we ought to be thinking this, and it isn't always grouping when it's four terms, and grouping problems are not always 4 terms. It could be 6, right? Heck, they could be, they could be 9. Basically any way that it groups together. Now, grouping actually comes from foiling technique. Because when you're foiling, what you may not recognize is that foiling is a shortcut for what I sometimes call double distribution. Okay, so let me just sort of do an aside here. So if we have double distribution, the whole thing is, if we have, let's say we have x plus 2 and x squared minus 1. Or no, let's do x minus 2 and x squared plus 1. Now, usually you would FOIL this, but foiling, like I said, let's just pretend that x minus 2, because we can do this, is a single quantity, and let's distribute it to both of these terms. And so I'm going to get x squared, x minus 2, plus 1 times x minus 2, and then I'm going to go through, so this was my first distribution, And if I do my second distribution by basically, within each of these terms right here, I get x cubed minus 2x squared plus x minus 2. Now, doesn't that look like your standard grouping problem? And so grouping is just basically, going in that direction, okay? So, and I'll give you one that's maybe just a little bit more far afield from there. So let's say I have 2a x squared plus bx squared minus 2a y squared minus by squared. Now remember, grouping is difficult when you have this negative right here in the middle. And there are actually ways of not having to deal with it. Sometimes you can actually reorder the terms. You actually could exchange these two terms as long as their sign goes with them. And if you do that, all of a sudden, oh my gosh, will you look at that? You don't have a negative middle term. So when you group, you don't have to worry about the sign, about remembering to change the sign of that last term. So from here, you have 2a x squared minus y squared plus b x squared minus y squared. And of course, this is two terms. I can pull out that x squared minus y squared, and I'm left with 2a plus b, but I'm not done yet. I have x plus y, x minus y, and then 2a plus b. Of course, if I were to leave it like this, I would have to, of course, change the sign once I put those parens in. And let me show you what I mean by that, just by way of review. If I have 2a x squared plus bx squared minus 2a y squared minus by squared, and let's say I didn't think of the possibility of changing the terms. Well, that's easy to group right there. Now you need to remember that this term right here is negative before I put the paren in. The moment that I put that in, 2ay squared becomes positive. So the actual drawing that paren right there is a functional factoring out of that negative 1. And if I factored a negative 1 out of that first term and change the sign, I have to change the sign of the second one as well. And that's the difficulty of that type, okay? Now from here, this winds up being, let's pull out an x squared, and I'm left with 2a plus b. Let's pull out a y squared out of that second pair, and I have 2a plus b. And so what you get is x squared minus y squared times 2a plus b, and that is, of course, exactly what we got in the other method. It was just we were pulling one of the binomials out instead of the other. But either way you do it, you get that. But when you're doing grouping, you got to watch the sign of that middle term. Okay. Now the last style of factoring that we need to talk about is, of course, the sum and difference of two cubes. Now, this, of course, was also recognized from a lot of multiplication. They recognized that when they multiplied things like a plus b in the form of a plus b times a squared minus ab plus b squared, let's go ahead and just basically when you do it this way, you can distribute the a plus b, and then you can do like 2 rounds of double distribution, or you can just take a and multiply it by all 3 of those, and then b and multiply it by all 3 of those. So let's take a and multiply it by every term in here, and we're going to get a cubed minus a squared b plus ab squared. And then when I multiply b by all of these, and that's positive b, I get plus a squared b minus ab squared plus b cubed. And just like the difference of two squares, they recognized that they had terms that were opposite signs, meaning additive inverses of each other, that were, of course, canceling out, and they were simply left with a cubed plus b cubed. And it was the same with the difference of two cubes as well. And so a cubed plus b cubed gives me the form of a plus b, and a squared minus ab plus b cubed, and then a cubed minus b cubed is a minus b, a squared plus ab plus, sorry, it's supposed to be squared, squared. And those are the two formulas, and it has everything to do with terms crossing out because they're additive inverses of each other upon multiplication. The same rationale for why the middle terms of the difference of two squares weren't there, right? The difference of two squares doesn't have that middle term because during the FOILing process, they canceled out. So if you have something like, I don't know, let's say 64x cubed minus 343, just to make it obnoxious, right? What is being cubed in the first term? Well, 4x is being cubed in the first term. What's being cubed in the second term? Well, 7 is being cubed in the second term. So if 4x is my a and 7 is my b, then according to the formula, it's 4x minus 7, 4x squared, which becomes 16x squared, plus a times b, so it's plus 28x, and then b squared is 49. And if you're struggling with, is that really the correct factorization, just remultiply it out. Check your answer. Like, I'm never going to be disappointed if you check your answer, okay? Now, those are all the different types of factoring problems that we've encountered in the factoring formulas. And of course, there are problems that mix and match and require you to use more than one method as you approach it. But in the videos following, I'm just going to do a bunch of examples, probably more complicated examples since you've seen them all before, but it'll just give you an excuse to work through some of these problems and just refamiliarize yourself with some of the factoring techniques and formulas that you just haven't seen in a little while, and just sort of get them back to the forefront of your mind, okay? If you have any questions, please do shoot me an email. Bye.